Thank you very much for the invitation. Hello, everybody. I'm Stéphanie ALLASSONNIÈRE. I'm a professor of applied mathematics in the medical school of Université Cité. I'm also a fellow researcher at the Prairie Institute, which is an AI cluster that has been selected by the French France 2030 fundings. So today I'm going to present a work that has been developed in collaboration with many people, in particular in Institut du Cerveau, Brain Spine Institute, ICM, from Pitié-Salpêtrière, and several of our PhD students. So we're going to talk about spatio-temporal analysis of manifold value data with an application to Alzheimer's disease screening. So first, I think you all have seen these curves earlier. These are the curves of the progression in terms of height of kids between 5 and 19-year-old. What is interesting is that we've been able to draw the characteristic evolution of the growth of kids and some deviation that are normal around this mean curve. This is a mean trajectory. I will call it not mean, but rather characteristic trajectory. So what is interesting is that we have the mean growth evolution. We have a reference time point that enables to have something that is very interesting. For each age, we are able to get the variability in terms of height. So these are actually the way people have collected the data, so to be able to draw the previous curves you've seen. So again, you have a reference time point, the age of the person, and then for each age, you are able to compute the mean and the standard deviation. This is interesting, but when you have that types of data, then you have a new element that comes into play, which are different clusters. Here, of course, you have girls and boys, so you still have a reference point, you are still able to pick an age and try to define the mean and the standard deviation. It would be easy if you would know who's who, but if you don't know who's a girl, who's a boy, then this is not well defined. And you have to face the fact that you are now having an heterogeneous population with unlabeled data. So, this is French. I don't know, everything should be in English, I'm sorry. So the notion that underlines all this is the notion of digital twin. So what is a digital twin? Here it's again in French. Everything I think else is in English. I'm sorry for the two mistakes. So what is the purpose of having a digital twin? Imagine you have a patient. Here is Anna coming. Anna is suffering from something. She's going to see the medical doctor who's collecting her personal lifestyle and clinical data. Then she has to go through other medical analysis, images, biopsy, whatever, goes back to the doctor so that you can try a first therapy. And then depending on how well this therapy fits, Anna will be fine, or Anna will have to loop again, go back to the medical doctor, try to better adapt the therapy. What is interesting with the digital twin is that as soon as we have all the data, we are able to design the digital twin of Anna so that on that digital twin, we can try to use virtual testing for multiple therapy, get the better outcome, try to see if this is patient-friendly. Of course, it really depends on the habits of the patient, and then update this reference, the reference model with the data that Anna came with, and then propose to Anna the best therapy at that specific moment with the specific features of Anna. So this is the way we're going to use the digital twin. Now the question is, how do we construct this? If you go back to the boys and girls, the digital twins are this. Well, they're not digital, they are paper twins, but still, if you have a kid that comes, given the fact that you know, for example, that this is a girl and that girl has been following the green mean curve for all age until 8, if suddenly there is a drop, a change in the dynamic, then you know that there is something that you should do. And this is how the digital twin enables you to better understand what's going on. And then a therapy can be put in practice and proposed to Anna. And then so that you will see the effect and you will see what will be the better therapy that enables Anna to go back to the green curve. So what is interesting is that paper twin has been already used and designed, but now we are working with other types of data. The first type of data are those type of spaghetti plate, where you have not something that is completely continuous and completely monotonic for each patient. Here you have the RESIST score, which takes the sum of the 5 biggest tumor length for a patient that suffer from cancer, and you see its evolution during time. And of course, you have different behaviors. You have still a reference point when the therapy is started, but then you have patients that are actually responding and then escaping, slowly responding, never responding, etc., etc. So you have to take into account all these types of behaviors. You can work with other types of data. Here you have shapes that have been extracted from MRI. This is the hippocampus. And you have several scans that are not here refer to a specific time point. If you think about this, this is Alzheimer's disease evolution, and Alzheimer's disease evolution is very difficult to handle because you don't know when the disease has started. So you don't have this reference time point, which means that the age of the person will not be relevant as an element of the statistical analysis. You can have, of course, multimodal data where you have the shape, the image, and some other types of things. And what you want to do is to compute this average evolution. How do you do that? You take all the data from your patient. Each patient is showing you a little window of the evolution of the long time evolution of the disease, the natural evolution of the disease. And what you do, you recombine everybody to get this average trajectory, mean evolution trajectory, which represents the population you are working with. And then, if you are able to do that, then you can use this element to produce the digital twin, so personalized to someone else, and then predict what's going on. So this is what we've been doing for these types of data using longitudinal data analysis and mixed effect model. So again, you have different subjects. You have the age, which represents the time, but you have different pace for acquisition, and you have, of course, different age for the first acquisition. What we want to do is really represent the trajectory of the data changes from this longitudinal data. And so if you look at the literature, if you have a temporal marker, so if you have a hard first time, let's say, birth or therapy started, etc., then you have many things that have been produced. And in particular, people can use regression because the time has a real meaning. But still, there is an issue, is that when you go back to the literature, most of these longitudinal data have been treated with linear mixed effect model. Okay, so everything that is linear. When you don't have access to this temporal marker, again, the age doesn't mean anything with respect to the age of the let's say, the anatomic age is not relevant with respect to the disease age. Then you have to work with something that is a little bit trickier, because the spatio-temporal distribution has to see whether you are comparing two persons that are similar in time but different in shape, or if they are similar in shape but different in time. Okay, so you have to be careful to have a model that will make the difference between those two scenarios. And we need to work, with something that is not a vector value data, but which are manifold value data. You're not working with vectors that are living in RD, but are with images, with shape, with scores that are bounded. And so you cannot work anymore with vector value data. So this is the model that we have been able to design. So this work was from the PhD thesis of Jean-Baptiste Chirati in collaboration with Aramis' team in Pitié-Salpêtrière. So what is this spatio-temporal mixed effect model? Each person has a specific number of observations, each observation living in a manifold. So basically, this is a non-flat space where the direct trajectory, so the mean path, the mean energetical path is not a straight line, it's a curved line because you have to go all around mountains or valley, etc. What we assume is that the representative trajectory is actually this lowest energy curve, which is called geodesic. So why is that interesting? Because the geodesic can be parameterized, although it lives in a high dimensional space, it can be parameterized with a first point, first time, and a first initial vector. This means that you go back to something that is finite in finite dimension. How do you map this toward each patient? First, there is a difference in terms of shape. The patient, the representative patient, is a little bit different from the observation. So you have a deformation of this representation to reach something that is close to your observation. And how do we do that? We have a vector on the manifold that shows us exactly where we have to shoot to have this point. Then, to have the whole curve, we are able to design what is called a parallel curve, which means that the patient eye will follow a curve that is parallel to this representative trajectory. This is somehow exactly what you have if you're thinking about the paper twin of growth. These curves are kind of parallel in terms of the geodesics that you have, the curve that you have, which is not a straight line. And now you can design the path of each of your new patient. Given this, as we said, we have a question of pace. So you may have some patients that are starting earlier or later, and you may have some patients that are having a more aggressive disease. So we need to reparameterize in time this curve so that if you think about this, the average speed being 1 and the T0 being that point, then each patient has a specific speed and a specific time shift that characterize the way this person is moving on this curve, on this particular curve. So what we do observe are only the points, so the y, I, j. So for each person I, we have j time points. So these are the initial dots that we had. And this is the transformation that we have, which is how they run on that curve, which is Ti, reparameterized in time. So what is interesting is that to be able to ensure the fact that you are not considering that this trajectory, this parallel curve has an impact on the speed of each person, you have to enforce orthogonality. And this is interesting because this geometric constraint also enables to have the statistical property of the model to be consistent. So this is invariant with respect to the geodesic. You have a time random variable now. So the time of the age of the person is not something that is a hard value. And if you summarize, which is a mixed effect model, you have fixed effects. So the population effect. So if you change, of course, these 3 parameters, you will change all the population. So this has an impact on the whole population. This is why it's called fixed effect. and the random effects, so what are patient-specific. The first thing is the accelerating factor, the time shift, and of course, this vector VI that you can see here, which is this what we call space shift, which actually is how different in shape the behavior of the patient is with respect to the representative trajectory. Right, so as I'm a mathematician, as I said, I will show you all the equation again. So here is the statistical model. You have on the submanifold observation that are following a trajectory which is the parallel curve of the representative trajectory. You have also this time reparametrization that we assume to be linear. And then, this is the model, you have all the hidden variables, so all these latent variables that you don't know for each given patient. So how speed and how early this person is moving. What is the difference in terms of clinical presentation this person behaves? So these are the hidden variable, and then you have the parameter to estimate. So what is interesting is that this model is, looks ugly, but mathematically speaking, it isn't ugly at all. It is quite interesting because we have algorithm that we can design to estimate the parameters given the initial observation. And these types of algorithm are the expectation maximization type algorithm. So just a quick review on how we do that. So you have this observation, you have these latent variable that you don't know, and the parameter you want to estimate. What you will do is trying to maximize the likelihood of the observation given the parameters, and you can work in the Bayesian framework, putting some priors on theta, which is actually relevant since we are working with a high dimension but low sample size. If you do the EM algorithm, you will produce a sequence of parameters that you will update in two steps. The first one being to compute the conditional probability of the latent variable given the observation and the current parameter. And the second step is the expectation of the complete log likelihood, which writes very easily with respect to this distribution. So although the model looks ugly, it belongs to the curved exponential family, which really simplifies everything in here. This term, this log term, actually comes to be something that separates the parameter and the random variables, so that when you take the expectation, you only take the expectation of the sufficient statistic that you have here with respect to the conditional distribution. And so at the end of the day, you just maximize this quantity where you take the expectation of the sufficient statistics. So this is the EM algorithm. Unfortunately, we're not able to compute the conditional distribution, so we're going to use sampling. So the stochastic version of this algorithm, which is called stochastic approximation EM. So instead of computing this probability distribution, you just sample from it and use a stochastic approximation of the sufficient statistic that you plug here into the argmax. And if you don't know how to sample, you can even move to the Monte Carlo Markov chain sampler that will enable you to just draw one element of this Markov chain. One is enough, as long as this Markov chain is at least subgeometrically ergodic. Up. And you can even go to something that is a little more efficient in practice. You can approximate this distribution in particular to be able to have something that escapes from local minima. And the only constraint is that you have a convergence towards the correct conditional distribution. So in practice, we have a very simple iterative algorithm that makes it easy to implement. So we are able to produce a sequence of theta that will at the end converge toward what we expect to be global maxima. We have the proof toward local maxima, and in practice, thanks to this tampering situation, we are able to escape local maxima. Right. If you face heterogeneity, what's happening? Well, it's extremely simple. We are able to do the clustering along the estimation. So the EM algorithm is easy to deal with mixture of those mixed effect models. It's just another line is this in this model that I showed you earlier. So if you go back to the model, which is right here, you just have to add a single line here, and that's it, making it very easy to move here and adapt. So there's no issue if you have heterogeneous population, as long as you know how many cluster you have in the population. And we are able to estimate the trajectory for each of the subpopulation at the same time of doing the clustering. Okay, what were we also able to produce are so as I said, the average trajectory is geodesics. What does it mean? It means that, for example, if you have a score that is that follows logistic curve, it will only increase, and you won't be able to deal with something that I've shown you earlier, which is a score that can decrease, and again, when the relapse occurs, it will increase again. So there's a little bottleneck here because we can only model something that is linear in terms of evolution. So not linear, but increasing in terms of evolution. So what we've been doing is also to try to have piecewise geodesic, and piecewise geodesic makes it enables us to really take this into account. If you have a piecewise geodesic, you can have a geodesic that will decrease, and then another one that will increase, and then the third one that will decrease again. So you are able to deal with these types of behavior. And so when my PhD student tried to do that, he was also able, with the same exact model of piecewise geodesic as you've seen earlier, to have heterogeneous population which have different curves, heterogeneous population that starts by the same behavior and one is escaping with respect to the other. For example, you have the flu that comes, and so safe people are evolving this way, and people who got the flu have another evolution. People that are starting from different points and converging, or having a single geodesic and some deviation at some point. So one single geodesic and people are escaping from this geodesic. So we have been able to design all these evolution, and everything is available in free open source software, which is called Deformetrica. And you have for the scores LISPy, which is still being adapted, and things are added in this LISPy version. So do not hesitate to go and try to use that. Okay, so in practice, what we've been able to do is for the anti-angiogenic response to the treatment, so we had that RESIST score that I showed you earlier, evolution with respect to time. The first time point is the first medicine that is taken by the patients. So we have a reference point. What we do not have is the time of relapse. These are these diamonds that you can see. And what we tried to do is to estimate this time of relapse with our models so that we were able to say to the medical doctor that it was probably time to have a new visit from the patient and change the drug, because you have, 7 or 8 different anti-angiogenic possible drugs. So it was time before relapse to try to change this second line of treatment. And so in terms of how good we were to estimate, as you can see, so in days, for a majority of the people, we were less than a month. And we were able also to see what is the correlation between the the factor of acceleration between the first response and the second part, which is relapse, against time shift. So you can see there seems to be something that is correlated between what happens before and what happens after the escape in time. So these are primary results on cancer. So again, we had to get new data and try to consolidate this. Going back to Alzheimer's disease, the question, oh, no, there's still a response. Going back to Alzheimer's disease, well, the question was, is there a special design of a population that is mixed? So there is an heterogeneity. The first part of the population is actually normal aging people. And the second one are the ones that are converting to Alzheimer's disease. So basically, we have people that are having along the study a diagnosis of Alzheimer's disease. So the question was, do we have a population that is rather this way, a single geodesic for the normal aging, and some piecewise geodesic where the time of break here would correspond to some time of diagnosis? Or do we have something rather like this? So you still have a normal aging geodesic, but somehow like a flu that you would catch the Alzheimer's disease and have a deviation that will start. So the question were, which one of these two models was the best one? And actually, it was quite difficult to know. So here you have the two volumes of the hippocampus on the two scenarios. So two different dynamics or one single dynamics and then one the disease people escape. So there was not really a consensus toward one or the other model. But what was interesting is that whatever model we would take, there is a high correlation between this rupture time when you have a change in dynamic and the age of diagnosis. And in particular, we were able to have something that is anticipating the age of diagnosis about 2 years. So which was quite interesting. And how did we use that? Well, we use that in a concrete way. Again, part of this is in French, but I'm sorry, we have now the platform in English, which is called docmemo.com, which is the expert of brain aging. And what did we do? We used that digital twin on different types of data. So we have the hippocampus I showed you, but also the atrophy of the gray matter, the score, the clinical score, which are standardized by medical doctors and scientific society. And you have the PET image as well to see what is the influence of the activation. What is the influence of the pathology on the activation areas of the brain? So basically we had that, and I can actually show you up. So here is it. And you have the whole patterns that is coming soon to see the evolution, exactly like you would have this paper twin for the evolution of a kid, where you can design something with you can, make a kid grow with respect to this curve. Now you have the exact same thing. So between 60 and 90, you have the evolution of all these modalities. And you can have the variability in the population with the pace, someone who is evolving more drastically, with someone who started much earlier, for example, or a different presentation of the pathology, which I would call different anatomy. So, of course, if I stop, you will see that the anatomy changes, for example, here. And the score in terms of clinical score is really the ordering of each score to deteriorate that is important. So you have here all this that you can fit. So if you have a new person that comes in the neurologist consultation, then depending on the age, for example, let's say 75, depending on the clinical presentation of the scores, I don't know, for example, something that is not that aggressive, but started quite early and with some presentation that is this way, we can have a pretty good understanding of what's going to happen afterwards. And how did we use that? We use that like this. If you have a patient coming, here are the average trajectories of the memory, language, practice, and concentration scores. This new person, remember Anna, comes into the neurologist's office. Then, thanks to the data that are collected with respect to Anna today, we are able to fit the model and predict some Alzheimer's disease diagnosis in 4 years. Unfortunately for Anna, she did 4 times the loops between being diagnosed. Okay, so again, we would have been able to anticipate at age of 77, and she has been diagnosed at 81. So basically, we have done several clinical studies. So this is the .fr, but you can go to the .com. And you can test your memory. You can try to ask to be included in clinical trials, because when you have that types of behavior, we are able to say if you are a relevant person to be included in clinical trials. And if you want to know what are the papers, where is okay, I know where it is in the French work. Notre approche. No. Yes, here are all the papers, all the clinical studies we've been doing to assess the relevance of the prediction that we are able to do. So basically, as I said, for Alzheimer's disease, we are able to anticipate in average of 4 years the deterioration of the patient. And it's about the same thing for Parkinson. We are 2 to 3 years, and for Huntington disease as well. So this is how the digital twin are used. And I think I'm over time and I'm done. Thank you.